This is the EdExcel AS Level Further Maths Paper 2 from the October 2021 series, and in this paper we will be taking a look at the Further Mechanics 1 paper. Question number 1. A small book of mass m is held on a rough straight desk lid which is inclined at an angle alpha to the horizontal, where tan alpha is equal to 3/4. The book is released from rest at a distance of 0.5 meters from the edge of the desk lid, as shown in figure 1. So that's what we see here. The book slides down the desk lid and then hits the floor that is 0.8 meters below the edge of the desk lid. The coefficient of friction between the book and the desk lid is 0.4. The book is modelled as a particle which, after leaving the desk lid, is assumed to move freely under gravity. For part A, we have to find in terms of m and g the magnitude of the normal reaction on the book as it slides down the desk lid. Now before we do anything else, we've been given information that tan alpha is equal to 3/4. And so, from that information, we can form a right-angled triangle. We've got 3, the opposite, 4 the adjacent, and through Pythagoras, 5 is the hypotenuse. And from this we can state sin alpha is 3/5, cos alpha is 4/5, and tan alpha, given to us, is 3/4. Now we need to find the magnitude of the normal reaction. The normal reaction would be shown here. Let's call it R. And then we've got the weight acting down like so. Here we have mg. We've got the mass m multiplied by gravity. This gives a weight of mg. And so if we resolve perpendicular to this desk lid, we can find out what R is. So, for part A, resolving perpendicular to the desk lid, R is equal to mg cos alpha. Now, we know what cos alpha is. We worked that out to be 4/5. And so we can conclude R is equal to 4mg over 5. Now for part B, we have to use the work energy principle to find the speed of the book as it hits the floor. Before we do anything else, we can find out the work done against friction. And so if we were to find out the work done against friction, the work done against friction is equal to the force multiplied by the distance. But the force is given by mu multiplied by r, and then we're going to multiply this by the distance. We know what mu is. That's equal to 0.4. We know what r is. That's 4mg over 5. And we know what d is. The distance it travels is 0.5 meters. So we can now find out the work done against friction. We have 0.4 times 4/5 times 0.5. It turns out we get 0.16 mg joules. So that's the work done against friction. Now we also have GPE as well. What is the total elevation? Well, we've got 0.8 meters, and then we've also got the vertical component here. which is 0.5 sine alpha. So the initial GPE then is equal to 0.5 sine alpha multiplied by mg, and then we also have 0.8 mg. So that will be the total elevation from here to here. And so if I work all of this out, knowing that sine alpha is equal to 3/5, we have 0.5 times by 3/5 times by mg plus 0.8 mg. It turns out, working this out, we would get 1.1 mg. Now, when it hits the ground, we've got final kinetic energy. And that's what we want to find, the speed of the book as it hits the ground. And so, the final kinetic energy is given by 1/2 times m times by v squared. We are finding v, and if I simplify this as a decimal, we have 0.5 m v squared. And so if we apply the work energy principle, the energy lost is equal to the work done against friction. So using the work energy principle, we have 1.1 mg minus 0.5 m v squared. This will equal the work done against friction, which is 0.16 mg. The m's would cancel out, so we have 1.1 g minus 0.5 v squared equals 0.16 g. So 0.94 g is equal to 0.5 v squared. So v is equal to, well, let's work out what v squared is equal to. 0.94 times 9.8 divided by 0.5. We get v squared is 18.424. And so if I solve for v, the square root of this is 4.29 meters per second, given to 3 significant figures. Question number 2. A particle of mass Em is at rest on a smooth horizontal plane between two smooth fixed parallel vertical walls, as shown in the plan view in figure 2. The particle is projected along the plane with speed u towards one of the walls and strikes the wall at right angles. The coefficient of restitution between the particle and each of the wall is E, and air resistance is modelled as being negligible. using the model for part A, we have to find in terms of m, u and e an expression for the total loss in the kinetic energy of the particle as a result of the first two impacts. Before we do anything else, we know E is equal to the speed of separation divided by the speed of approach. Now, what we can do is find out the speed of separation after the first impact before we do anything else. So, it approaches this wall here with speed u, and if we say that it rebounds off the wall, and then moving off over here, we would have speed v, say, and we can find out what v is. So we have E equals v over u, which is the speed of approach, from which we can conclude v is equal to E multiplied by u. So we have EU. So what is V equals EU representing? Well, it would represent the speed after the first impact. Now, after that, it approaches this wall with speed EU, and so it would rebound off the wall with speed W, say. And so what we now need to do is find out what W is. So we know that E is equal to the speed of separation, which we just said is W, and then we will divide this by the speed of approach, which we have just said is V, which is EU. And so therefore we can conclude W is equal to E lots of EU, which is E squared U. So it rebounds off this wall with speed E squared U. And so what is W equals E squared U representing? Well, it's representing the speed after the second impact. Now, what exactly do we need to do in this question? We need to find an expression for the total loss of kinetic energy. So therefore, if we say that the kinetic energy lost is K, we have 1/2 multiplied by the mass of the particle. Now the mass of the particle is given by Em, and then we have the original speed, which is u, and then we square this, and then we subtract off 1/2 Em multiplied by this final speed, E squared U squared. And so if I tidy this up, I've got 1/2, and then I have an M and a U squared common, and then I will multiply this by E minus e to the power of 5. That comes from the fact we have E times E squared times another E squared, which is e to the 5. Now for part B, given that e can vary such that e is in between 0 and 1, and using the model, we have to find the value of e for which the total loss in kinetic energy of the particle as a result of the first two impacts is a maximum. We're given that e can vary. And so, if e can vary, with this information, we can find out what dk over de is. And that's because e can vary. And if I differentiate the result here, I have 1/2 mu squared lots of 1 minus 5e to the power of 4. We are looking for the rate of change of k with respect to e to be a maximum, and it's a maximum when dk over de is equal to 0. So in other words, we're going to set the result here equal to 0. We've got 1/2 mu squared lots of 1 minus 5e to the power of 4 equals 0. So, dividing both sides by 1/2 mu squared, they're just constants, we end up with 5e to the power of 4 equals 1. So, e will equal 1 divided by 5, and then we will take the fourth root of this. So if I work this out, e is equal to the fourth root of 1 over 5, which is 0.67 given to two significant figures. Now for part C, we have to describe the subsequent motion of the particle. First of all, the particles will continue to bounce off each wall indefinitely. So once it goes back to this wall, it goes back here, and then it goes back here, and so on and so forth. But what would happen each time, because E is in between 0 and 1, for the next bounce we would have E cubed U, and so on and so forth. So for higher powers, the speed would be decreasing, and so we can say then the speed of the particles decrease. And that's because E is in between 0 and 1. Question number 3. The total mass of a cyclist and his bicycle is 100 kilograms. In all circumstances, the magnitude of the resistance to the motion of the cyclist from non-gravitational forces is modelled as being kV squared newtons, where v meters per second is the speed of the cyclist. The cyclist can freewheel without pedalling down a slope that is inclined to the horizontal at an angle alpha, where sine alpha is equal to 1 over 35, at a constant speed of v meters per second, when he is pedaling up a slope that is inclined to the horizontal at an angle beta, where sine beta is equal to 1 over 70, and he is moving at the same constant speed v meters per second, he is working at a constant rate of p watts. For part A, we have to find p in terms of v. Now before we do anything else, I think it will be a good idea to draw a diagram to help picture what's going on. Here is our diagram. When he is going down the slope, he doesn't need to put any work in. The only thing helping him go down the slope is gravity. Opposing that is the resistance kV squared at speed v equals v. So far we don't know anything about what's happening when he's going horizontally, but when he's going up the slope, he's going forward with a force of D. Opposing him is a resistance of kV squared, where V equals V. And in both circumstances, we've got the weight of himself and the cycle being 100g, as we see here. So, to help do this question, we need to use mass equals force, the sum of the forces is equal to the mass times by the acceleration. So, if we consider the situation for going down the slope, we have 100g sine alpha acting only. We subtract the resistance kV squared, and because we have constant speed, there's no acceleration, so mass times acceleration is 0. So this is the situation for going down the slope. And if I call this equation 1, we'll leave that alone for now. We can now find out what the situation is when we go up the slope. So going up the slope, we've got D going forward, and opposing that is the gravitational effect. So we subtract 100g sine beta, and then we subtract the resistance kV squared, and again, because we've got constant speed, this is all equal to 0. Now before we do anything else, it may be a good idea to right now substitute in the values of sine alpha. Sine alpha is 1 over 35, so we've got the situation for when we go down the slope being 100g over 35 minus kV squared equaling 0. We'll call this equation 1. And what we have here is the situation for going up the slope. And knowing that sine beta is equal to 1 over 70, we've got D minus 100g over 70 minus k v squared equals 0. Now, if I call this equation 2, what we can do is replace the kv squared by a certain value by rearranging equation 1. From equation 1 we can rearrange to say that k v squared is equal to 100g over 35, and if I call this equation 3, what I can do now is substitute in equation 3 into equation 2. So I've got D minus 100g over 70 minus k v squared, which I've just said is 100g over 35. This is all equal to 0. And if I solve for D, D will equal 30g over 7. What else do we know? Well, we know already that power is equal to the driving force, D, multiplied by the velocity, V. And so, using that idea, we can conclude that P equals D, which is 30g over 7, multiplied by V, So the power will equal 30 times 9.8 divided by 7, which is 42V. So P equals 42V. And now for the next part of the question, if he pedals and works at a constant rate of 35V watts on a horizontal road, he moves at a constant speed of U meters per second. We have to find U in terms of V. So for us to find out what U is in terms of V, let's think about the situation horizontally. Well, we know he works at a rate of 35V watts, so that means going forward we can find out what that force is. Now we have to consider the situation when we're cycling at a speed of U meters per second. So for part B, if I use the fact that power is equal to driving force times speed, I've got the power 35V, and this is equal to the driving force. We'll call it Q for now. Let's just color coordinate this. We'll call this Q, and then we multiply this by U because we are traveling at a constant speed of U. And so we can conclude from here Q is equal to 35V over U. So we have 35V divided by U. So that's going forward, and opposing that would have a different opposing force. Instead of us having V, we would have K U squared. And again, what we can use here is the fact that sum of the forces is equal to mass times acceleration. So using the fact that the sum of the forces is equal to mass times by acceleration, we have 35 V over U, and then we subtract K U squared. This is all equal to 0. Now I need to find out what U is in terms of V, so I need to find out what K is. Now, can I find out what K is? Well, I can use equation 3 to help me find out what K is. So from equation 3, we can rearrange to say that K is equal to 100 G over 35 V squared. So that's what K is. Now, if I call this equation 4, and if I call this equation 5, what I can do is substitute in equation 4 into equation 5. So I've got 35V over U minus K, which is 100G over 35V squared multiplied by U squared. This is all equal to 0. So we need to simplify all of this. Now if I multiply by V squared, I have 35 V squared, and if I multiply by U, well, before I do that, what is 100 divided by 35? And if I times this by 9.8, I will have 28 U cubed. Rather, this is cubed. And this is all equal to 0. So now I need to find out what u is. So if I rearrange this, you can see u cubed is equal to, well, I'd have 35 divided by 28, which is 5/4. So u cubed is equal to 5/4 v cubed. And if I cube root this, we can conclude the cube root of 5/4 is 1.08 v, and that's given to 3 significant figures. Question number 4. Two particles P and Q have masses m and em respectively. The particles are moving on a smooth horizontal plane in the same direction along the same straight line. When they collide directly, the coefficient of restitution between P and Q is E, where E is in between 0 and 1. Immediately before the collision, the speed of P is u and the speed of Q is eu. For part A, we have to show that the speed of Q immediately after the collision is u. Here I have drawn a diagram to illustrate what's going on. We've got the situation before. P moves off with speed u, and then after it's got a speed vp. We don't know what vp is. And similarly for Q, it moves off with speed eu, and then it moves off after with speed vq. We don't know what vq is. Now, if I use the idea of conservation of linear momentum, I have m multiplied by u plus em multiplied by eu. This is equal to m multiplied by vp plus em multiplied by vq. So, noticing the m's cancel out, we end up with u plus e squared u equaling vp plus e vq. And if I factorize out a u, we've got u lots of 1 plus e squared equaling v p plus e v q. Now let's use Newton's law of restitution, which we know that E is equal to the speed of separation of the speed of approach. And if we take a look at our diagram, you can see the speed of separation is vq minus vp. The speed of approach is, well, that will be u minus eu. So we've got u minus eu. And if I multiply both sides by u minus eu, we end up with e lots of u minus eu equaling vp, rather vq, minus vp. Now if I call this equation 1 and this equation 2, I can find out what vq is. Now what do we need to do in this question? We need to show that the speed of q, which is vq, immediately after the collision is u. So I need to eliminate the vp's, and I can do that by adding equation 1 and equation 2. The reason for that, the vp's will cancel out. So on the left hand side we've got u lots of 1 plus e squared plus e lots of u minus EU, and that's equal to VP minus VP, which is 0 VP, and then we have EVQ minus, rather, EVQ plus another VQ. So let's see if we can tidy up all of this. Well, let's expand the brackets. We've got U plus E squared U plus EU minus E squared U equaling EVQ plus VQ. With the E squared U's cancelling, we are left with U plus EU equaling EVQ plus VQ. Now let's factorise on both sides. We've got U lots of 1 plus E equaling VQ lots of 1 plus E, from which we can conclude VQ is equal to U. In other words, VQ has the same speed as P before. Now for part B, we have to show that the direction of motion of P is unchanged by the collision. Well, what we want is VP to be greater than 0, and that will imply that the direction of motion is not changed. So, what I'm going to do for part B is find out what VP is by using equation number 1 over here. So I will be using the equation over here. However, I will replace VQ with U. So I've got VP equaling U lots of 1 plus E squared minus EU. I've got U plus U E squared minus EU, and if I factorise out a U, I've got U lots of E squared minus E plus 1, and I need to show that this is greater than 0. Well, one way we can do that is to simply complete the square. So if I complete the square of what's inside the bracket, I would have E minus one half all squared, and then I'll subtract off the square of 1/2, which is 1/4, and then I will add on 1. So this is what E squared minus E plus 1 is equivalent to. So I've got VP equaling U lots of E minus 1/2 squared plus 3/4. Now, what you need to know about all of this is all of this is going to be greater than 0, because E minus 1/2 all squared is greater or equal to 0. Adding on 3/4, this entire bracket is going to be greater than 0. And so what can we conclude from that? Well, we can conclude that P continues to move in the same direction because VP is greater than 0. Now for part C, the magnitude of the impulse on Q in the collision is 2/9 mu, and we have to find the possible values of E. Well, here we need to use the impulse momentum principle. So if I use the impulse momentum principle, I have I, which is equal to the mass. Well, here we have to use the mass of Q, which is Em. And then I'm going to multiply this by change in velocities, so I've got u minus EU. Now I know what I is, that's 2mu over 9. And this will equal what we have here. It equals EM lots of u minus EU. And noticing that the u's and the e's cancel out, we are left with 2 over 9 equaling 1 E. Rather, the m and u's cancelled, so we are left with 2 over 9 equals E minus E squared, which I can write as 9E squared minus 9E plus 2 equals 0. So factorising, I have 3E minus 1 lots of 3E minus 2 equals 0, from which we can conclude E could either equal 1/3 or E could equal 2/3.